Okay, welcome to your Chapter 11 introductory video. One reason we saved Chapter 6 for Gen Chem 2 is that it pairs really well with Chapter 11. Chapter 11 is properties of solutions, their concentrations, and colligative properties. Colligative properties are properties that depend on basically the number of solute particles in the solution. And it's independent of their identity, so it really is dependent on their sheer numbers, and that can be expressed in different ways of expressing concentration. So learning goals for this chapter will be initially, one of the first things you'll see in your chapter as you read it is the idea of osmosis and what that is. Secondly, we'll talk a lot about vapor pressure. You'll need to understand it, get a strong understanding of it conceptually, but also be able to do some calculations involving Raoult's law. And then you'll also look at freezing point and boiling point changes as a result of this colligative properties. We'll also define molality. Molality is different than molarity with an R, so we'll be sure to distinguish those two. And ultimately, we'll need to be able to calculate changes in boiling points and freezing points. So the first thing in your chapter is reverse osmosis. The easy way to talk about reverse osmosis is just by showing a figure. On the figure on the left here, you see seawater on the left, and then normal saline water, if you will, on the right, so maybe fresh water. And what happens ultimately is you have a net movement. The key to this phrase here is that it's net movement of water from right to left. It does not mean that water cannot move from left to right. What you have here is a semi-permeable membrane. That membrane is permeable to water, but it's impermeable to the salts, to the ions in solution. Just basically has to do with size. What you have to realize is you might think that a sodium ion must be smaller than a water molecule because a water molecule has 3 atoms and a sodium atom's only 1. But it turns out that the ions in solution, because of their charge, are heavily hydrated with waters. That means they're surrounded. They attract waters. So a sodium ion will probably have 6 waters surrounding it, which makes it much larger than an individual water molecule. So you do have a net movement of water from right to left. And it really is just a statistical process. You can imagine me having 2 cylinders of gas connected by a port. Okay? And on the left, let's just say I have hydrogen gas and I have very few hydrogen gas molecules. And on the right, let's just say I have oxygen gas molecules. Let's say I have a lot more oxygen. Now, once I open this port, you can imagine that we're going to get a lot more movement of oxygen in this direction than we will get hydrogen in this direction, just based on sheer numbers, until the system kind of comes to what we call equilibrium, kind of normalizes itself and becomes much more uniform. You should be able to understand that from just a sheer statistical approach, and that's what we're seeing here. Same thing. Ultimately, the water will stop rising because there's another force acting here, and that's obviously gravity. So the water's just not going to rise indefinitely, of course. And now you can imagine that the force pushing down here, gravity, and that we've increased the number of water molecules on the left now because a lot have moved from the right to the left, we reach what we call this kind of equilibrium point. Now the net movement of water molecules is balanced. This is osmosis. Well, we can take this principle and apply it actually to making drinking water from seawater. And that is, you can just apply a pressure, and they do this with all different ways, but I don't want to go into those in detail. You can read about that. But you can apply a pressure here that's greater than the osmotic pressure. The osmotic pressure is calculated basically from this height difference here. And the actual information in your textbook will explain that calculation, but you're not responsible for doing any calculations. That's why I'm not showing the equation. We can actually apply a pressure greater than the osmotic pressure, and what you wind up do is getting fresh water over here, and basically you're left over with just a salty brine over here, and this becomes, drinkable water. And we use that process for making water. Okay, one of the major concepts in your textbook is vapor pressure. And let's imagine I have a glass of water. If you put a glass of water on the counter in your kitchen, you come back in a few days, it might be gone, right? The water will have evaporated, and you might be left with some salts sitting at the bottom of your glass, because the salts do not volatilize because they have a much lower vapor pressure. Substances that are considered volatile, that word means they have a significant vapor pressure at a given temperature. So vapor pressure is, if I put a lid on this glass of water, it's the pressure that we have in the gas phase here with the vapor when the system comes to equilibrium. Just like with reverse osmosis, we see that we have a point at which the net movement is balanced. The same thing here. When I first put that glass there, I'm going to have evaporation of water and a little bit of condensation. Ultimately, the rate of evaporation and condensation becomes the same. Whatever that pressure is here is called, more correctly, the equilibrium vapor pressure, actually, than just vapor pressure. And substances that are volatile, we say have high equilibrium vapor pressures. So you see that here now, with this graph, we have 4 different substances here. And this, let's just compare. Here's water right here. Okay, you can see now that's what we call the normal boiling point. The normal boiling point is the temperature at which the equilibrium vapor pressure equals the atmospheric pressure. So in this case, we're doing just normal atmospheric pressure, 1 atmosphere here. Remember, that's equal to 760 millimeters of mercury, or 760 torr. So 100 degrees C is the temperature at which water's vapor pressure equals 1 atmosphere. And you can see for a substance down here, diethyl ether, it is a much more volatile substance. And it's only 34.6 its temperature at which we have to reach where we can get that vapor pressure equal to the atmospheric pressure. So a substance that is more volatile has a lower boiling point. This substance out here is not very volatile at all. So you can think of it as its vapor pressure. Let's look at all these substances at this temperature. This one's vapor pressure, let's just say it's 1. I can't even read it. It's a very low vapor pressure at that temperature. So you have to increase the temperature all the way up to 197.3 before you can get that vapor pressure to 1 atmosphere. That's an important concept. I need you to look at this graph and really spend some time thinking about it. So you can actually use the concept that different substances have different vapor pressures and different boiling points to separate them out. And that's what fractional distillation is. And that's something you'll actually do in organic chemistry. In the lab, you'll do some sort of distillation experiment. But we use this to actually separate out oil. Crude petroleum, crude oil, has many components. Some of that's gasoline, as you can see. Some of that might be a diesel oil. Some is lubricating oil. What we do is we heat it all up, all but the really heavy stuff, the asphalts and tars and things like that. It boils, right? And then it condenses at different temperatures, and we separate it out. And we collect the fraction that condenses, here. Then we collect another fraction here. That's how we get different fractions from our petroleum. Now, so what we can do is we can actually calculate vapor pressures of solutions. And what you simply do is you sum up all the individual vapor pressures of each component. So looking in this equation here, X is the mole fraction, okay? So this would be the mole fraction of substance 1, and that substance, equilibrium vapor pressure. So if you had 2 substances and you had their mole fractions and vapor pressures, you could figure out what that total vapor pressure of that solution is. And this only applies to ideal solutions now. So let's say we had a mixture of 60% water and 40% benzene. Well, we do 0.6 for water times water's vapor pressure. Then we do 0.4 for benzene times its vapor pressure, and add those 2 together. That gives you the total vapor pressure in that space above that mixture that you're looking at. Only works for ideal solutions, just like we did with ideal gases. That means substances in which, the concentrations are not too high and the particles are behaving ideally. Well, we can actually apply Raoult's law. Let me go back here. There is a question on smart work I gave you. So, imagine you now have two substances and you calculate the total vapor pressure. There's a question on smart work where I ask you to calculate the mole fraction of one of those species in the gas phase. Well, if you know the total, right, you can calculate the vapor pressure in that phase, that part of the total, for one of them. You divide this by the total effectively, and you can figure out a ratio of how much of that total vapor pressure is contributed by one of those components. So give that a shot on smart work. Now we can apply Raoult's law another way also, and that the difference here is, in this case, all of these substances are volatile. They all have significant vapor pressures. Here you notice what we're going to do is we're going to apply Raoult's law a different way. We're going to add a non-volatile solute. So now imagine I add sodium chloride to water. Okay? Let's say the sodium chloride is present at 0.1 mole fraction, or 10%, and it's 90% water. You can calculate the vapor pressure of that solution. We're assuming the sodium chloride doesn't contribute to the vapor pressure because it's non-volatile, by simply knowing the mole fraction of water and the vapor pressure of water. The key here, a lot of students struggle with this, is that if you're given a question and they give you the mole fraction of sodium chloride as, say, 0.1, you don't put that 0.1 into here. It's for the solvent. You put 0.9 into here, and then the vapor pressure of water. That's one of the keys to using Raoult's law here, is not forgetting that. So what we see is two things that happen. We'll spend some time on this in class. We'll look at a graph. We see boiling point elevation as a result of adding a solute. So if you're cooking pasta at home and you put salt in your water, which you should, the presence of that salt causes the boiling point to elevate. And it has to do with, see if I say it here, the decrease in the vapor pressure. Yes, it has to do with the decrease in the vapor pressure. By adding salt, you decrease the vapor pressure, therefore you raise the boiling point. And we'll talk about that in detail, so do some reading on that in your book. So the other thing you see is freezing point depression. Now we can lower the freezing point of a substance by adding salts, and this is what we do when we salt our roads. It lowers the freezing point of the ice. So instead of the ice freezing at 0 degrees C, now it has to freeze at 10 degrees, minus 10 degrees C, right? And if the temperature outside is 5 degrees C, well, guess what? Then your ice starts to melt when it wouldn't have melted. Negative 5, I should say. So that's freezing point depression. Okay, so now we need to talk about molality, and you'll see this in your book in great detail. And the only difference between this and molarity, which is with a capital M, that's molarity. Molarity was volume of solution, remember? Now, not only are we not using volume, we're using mass, and not only are we not using solution, we're using solvent. So mass of solvent. So with molarity, you would take, I've got, this many moles of sodium chloride in this much water, and then the total final volume is 1 liter, so therefore this is my molarity. Now we're going to be using the mass of the water itself, not the mass of the solution. That's incredibly important because some of these things that we're talking about, these properties, depend on temperature. And if you use molarity, well, volume is dependent on temperature. Volume takes up more space at a higher temperature, so you don't want to use volume of solution. By using mass of solvent, that is independent of temperature. And when you're dealing with very precise analytical solutions, that's critical. This is just a little schematic you can use. I usually give these because books give them. I don't use them much, but if this works for you, great. Just showing you, hey, don't forget you can use density sometimes if you're given a volume and you need to get to the mass. So keep that in mind. And of course, you can always use your molar mass. Lastly, there's going to be two things in your book about doing calculations involving boiling point elevations and freezing point depressions. I don't have a slide for freezing point depression because the equation is basically the same. If I remember the notation, it's equal to KFI times M. Now this is molality. You cannot use molarity here, okay? This is a constant that's given to you. These are both constants that will be given to you. You can look those up, or if maybe they're going to ask you to calculate that, but that's rare. Question is, what is I? I is the Van Hoff factor. It's introduced at the very beginning of your chapter, but I haven't talked about it until now. I is basically the numbers of particles in solution. So if I have a 1 molar solution of sodium chloride, ultimately when that goes into solution, I wind up with 1 mole of sodium ions and 1 mole of chloride ions if I have a liter solution, right? So that's what the I factor is. It tells you the number of particles because that's what's important with colligative properties, the numbers of particles. So this is very important because if I have a salt like calcium chloride and I have 1 molar solution and I have 1 molar solution of sodium chloride, well, this actually has a better colligative property. It will lower the freezing point more. It will raise the boiling point more because the I value here is 3. For sodium chloride, it is 2. So when we salt roads, guess what? We don't use sodium chloride. We typically use calcium chloride. Why? For this very reason. We will get a freezing point depression that is greater with a salt that has 3 ions. Okay, so that is your video for Chapter 11. That is my last slide. So I will see you in class, and make sure you read your book and start looking at this material.